All right, we're back at the Xanadu Quantum Codebook, and we will be continuing exactly from where we left off, which is section 8I, which is introduction, if I remember correctly, 6. So previously we were talking about phase things, Z gates, S gates, T gates, but now I think we're talking about more general rotations. So we see a general sort of framework of one qubit over here, the common block sphere representation. Note that we can see that each rotation is a rotation about that axis. So RZ does nothing on the 0 state. These are just the gates for Rx and Ry. By the way, Rx of theta equals x is pi because it's clearly a 1 pi rotation. Yes. All right, so we'll get right into the code sort of section. It's been a while, actually. I guess since the last video that I've actually done anything in Penny Lane, so might be a little rough, but we'll get into it. So first we have to apply an Rx gate with an angle of pi to the computational basis gate, or to one of the computational basis states. Oh, okay, so we want to qml.rx 1pi.pi return qml.state. Oh, right, I always forget. Wires equals 0. All right, off to a promising output. You should have noticed the case Rx equals pi up to a global phase of -I, but what does Rx do more generally? How does this affect the amplitudes? Implement a Q node that applies the Rx with parameter. Oh, okay, so we're just going to plot the amplitudes of 0 and 1 after applying the Rx gate. Well, this is easy. It's the same code as above, qml.rx theta wires 0 return qml.state. Right. So we can see that this is the 0 state imaginary component. This is 0 real state, right? So if it starts in 100% the what am I trying to say? It starts in 100% of the 0 state. Then at 2 pi, which is right around here, it'll go all the way back around. Notice the amplitude is -1, but that the probability of measuring it in a 0 state is 100%. So you can see how this has a sort of trigonometric sinusoidal sort of representation. And this is just explicitly quantifying this. It's periodic. Repeat the above exercises, but do Ry. So it's the same sort of principle. All right, let's see what this yields. You can see a similar sort of pattern. Here's the 1 state. In fact, it's the same pattern. However, the 1 real state, which over here, 1 real is in this line. We can't it lines up, so we can't see it. The 1 real state is now right here. So this influences the real states rather than with this, I in front of it. All right, next one. We're moving on to the universal gate set. All right, recall the most general expression, the U3 gate is that. We can also decompose it into RZ, RY. It's RZ, RY, RZ. So right here of 3 different parameters. I'm not going to prove that. It's the same sort of idea, RZ, RX, RZ. Yeah, so this is a universal gate set, which means that we can make any unitary. We're a single qubit. You can also do this with just H and T. So what do we do here? Can you find the set of angles phi, theta, omega such that the sequence of gates RZ, RX, RZ acts the same as a Hadamard gate? Well, see, now I have to remember. Oh, actually, no, I don't have to remember. If we know that a Hadamard gate is changing it from the Z basis to the X basis, then we know that this is 0. So we want to map to 0 state to the 0 plus 1 state. So we'd have to do a rotation around X of numpy pi over 2, because that'll take us to that state. And then, let's see, I'm just trying to think. So if we want to map the 0 plus 1 state to the 0 state, which is what if we apply a Hadamard gate it does, then we do 0 plus 1 is there, rotate around pi, and then Z. Okay. Don't know if this is correct, but this is going to be my first guess. No. All right. That works in that case, but maybe we need to, let's see, that maps 0 plus 1 to 1. Oh yeah, that makes sense. We need to do that'll change nothing. Just trying to think of how we would map the 0 plus 1 state. So doing any sort of RZ rotates around there. Oh, I see. We want to rotate the RZ, so now it's in the Y plane. So if we rotate the RZ, so now it's in the Y plane. Pi over 4, pi over 2, sorry. Then we do an X rotation of negative. And then maybe this can be 0. Let's see if this is right. No. Let's see, that works for the 0 plus 1 case because we have 0 plus 1 goes to let me just bring it up. Let's see. So if we have our 0, it's probably easier to draw a little sphere. So, right, we have our sphere, and so this is the X, this is a Y, this is the Z. Not a great sphere, I know. So this is the 0 plus 1 state right here. So now what we're saying is rotate around the Z. Oh, maybe this has to be negative. Hold on. Maybe this is negative. No. Okay, so we're rotating. Why is it? What is going on? Why is this doing this? Okay, so we're rotating around this way. So we want to rotate by pi over 2 to here. And then if we rotate around X, X is going around this way, so we want to go back up to here. All right, so let's consider the 0 minus 1 case. Actually, that's probably all the cases. Let's consider the 0 case. So we do RZ, which changes nothing, RX, which maps it to here, And then, okay, so this should be numpy dot pi over 2. Let's see. Okay, this is not right. So in this case for 0, why does it keep doing this? This website is very annoying. For 0, right, the RX, the RZ gate at first does nothing. The RX gate maps it to this state, pi over 2, which is just the plus y. And then the RZ maps it over here. So it works in that case, but now we need to think about, maybe let's think about the one case. RX maps it up to here, maps over to here. That seems right. Maybe there's just some sign I'm messing up. Oh, yeah, there's just some sign. I guess RX goes the other way. That's my bad. So RX actually goes around this way instead. Okay, that was just my bad. I didn't realize what it was doing. There probably was an easier way to do that, but that was just my method. All right, moving on. Using the previous exercise, rewrite the following circuit over to gate set RZRX. Recall it is okay for you to work up to global phase. So we know that, I'm just going to copy this actually. We know that the H gate is the pi over 2, pi over 2, pi over 2, numpy dot pi over 2, numpy dot pi over 2, numpy dot pi over 2, and then we know that the S gate is a rotation of pi over 2 as well, I believe. The T gate is pi over 4, am I correct? I think that's right. And then the Y gate is pi. All right, what are the odds that this is right? Oh, I have to decompose RY into RZ, and I have to decompose a Y gate, so that's a complete rotation around the Y axis. So maybe I should just get a new one. So if we have, what it's been, our little drawing, that's actually the center. A complete rotation about the Y. So this is Y. So that would map this to this, which would be, or this to this. So that's a rotation about X and a rotation about Z. So in this case, it's our Z of pi or X of pi. Is that, that's just an XZ. Is that, am I crazy? Let me see if I'm crazy. Yeah, I'm crazy. Okay, so in general, the Y gate, I'm trying to, the easiest way to do is just to look at the matrices, but I really don't want to have to look at the matrices. But I guess I'll do that. So we go to poly gates, go over here, and then we do rotation gates. Then we go, so poly Y, it's that. Let's go over here. Actually, are the rotation gates? No, they don't even have them. Okay. Rotation gates. Rotation, rotation, rotation. Wow, why is it so hard just to get the list of rotation gates. Ah, here we go. I don't want to deal with that. All right, so the RX gate. So this we want to be, and then the RZ gate. All right, so we want these two to match. So we want this to be oh, why do I have to actually deal with these matrices? So we want to make this 0, negative I 0 equal to, I really do not want to solve this system of equations. Let's see, suppose this is pi over 2. Let's just take a guess. Maybe, I know it's going to be something like that. So then we have pi over 2 is 0, I, negative I, 0. And then we need this, which is going to be suppose this is pi maybe, so this is just 1, 0, 0, negative 1. So we do row times column, we get 0, row times column, row, column, we get I. Oh, maybe this should be first. Maybe what happens if we do this first? 1, 0, negative 1 times 0, negative I, 0, we get row times column, we get 0, we get row times column, we get negative I, row times column, I 0. There we go. So it's RZ of pi, RX of pi over 2. All right, and where yes, this is correct. Okay. All right, well, we know this is right. Maybe this, yeah, maybe I messed up T and, okay, I did not. I don't remember what the, oh, that's because this needs to be RX gate. That's, now this should work. Okay, it doesn't work. Oh, it's T dagger. Okay. Okay, I'm just, what's going on here? Okay, I need to look up what the T and the S gates are. I don't remember their matrices. I think they were on this link. Here we go. The I, S, and T gate. The S gate is equal to yeah, pi over 2. T gate is pi over 4. Oh, but it's just the phase. Let me see. T gate RZ. See if that comes up. Yeah, I was right. The T is equivalent to the RZ for angle pi over 4. All right, so these are right. Okay, so is my this decomposition wrong? Let me check. Decompose Y gate RZ RX. What are the odds this exact same link has it? Standard 2-qubit decomposition of 1-qubit gates. Let's look at that. No, that's not what I wanted. Let's see. Okay, so ry of pi is what we want, right? So we have rz of 2 pi does nothing. Rx, oh, this be, oh, I was right all along. Okay, well, I confused myself. Let me look at this again. Okay, the RZ gate. I don't care about the RX gate. Because it's 1/2 theta, right? Because I was doing this as if sine of pi over 2 is what I wanted, but I want sine of pi, which is what I want. However, it's pi over 2 times 1/2. All right. It's possible to do the above using only 4 gates. Yeah, we can cancel a lot of them out. That makes sense. 2 H and T gates are also a universal gate set. By combining just these 2 gates, we can achieve arbitrary precision on any single qubit operation. Right, a penny lane operation that uses 6 H and T. I do not. This seems like something that would be automated. All right, so takes the 0 state. Okay, well, let's see if we can just guesstimate what's going on here. So we have H. I really don't want to do this. Oh, yeah. Why is it making me do so much matrix multiplication? Okay, yeah, so 2 H's are the same. So what are the odds we can guess and check our way into this? Okay, this is not correct. I just want to... Couldn't remember if it's capital or lowercase. Oh, right, it's Hadamard for some reason. Wait a minute. What's the... That doesn't seem right. I just put a single H and it said it was correct. Let me see this. Maybe everything cancels out. 1 plus e to the I pi over 4 cosine of pi over 4. Let me look up. No, I don't need to look that up. Okay, so maybe I gotta do this out because I'm just curious now. Let's see. So we have 1 plus e to the I pi over 4 minus, sorry, plus I 1 minus e to the I pi over 4. Okay, so we can write this as 1 plus cosine of pi over 4 plus I sine of pi over 4 plus I 1 minus cosine of pi over 4 minus I sine of pi over 4. Distribute the I, so we now have, let's see, we now have, over here we have plus I minus I cosine pi over 4 plus, because I times I is -1, plus sine of pi over 4. Pi over 4 is always 1 over square root of 2. So now we have 1 plus 1 over square root of 2 plus I over square root of 2 plus I plus, sorry, minus I over square root of 2 plus 1 over square root of 2. So we can combine these two to get, let me see, where's this eraser? No eraser anywhere. Okay, I guess I'll just write it up here. So we have 1 plus, so we can combine. This should be a negative. We can combine these two, cancel out. Yeah, this is a separate thing. This, so we have 1 plus I plus 2 over square root of 2. I mean, I guess maybe I feel like this I should be canceling somewhere. But I don't know. I guess, yeah, I guess it just reduces down to H. Or there's like a bug right here. Let's see. Maybe it's a glitch. Maybe this isn't even equal to it. Yeah, I need to check the... I feel like I need to do the math now. This is so weird. So we have H, T, H, T, T, H. Those are the correct ones. Okay, am I... Okay, let me see. Let me see if I'm just going crazy. So we have our 2 by 2 matrix that we're trying to multiply here. So H is 1 over square root of 2. Or is it negative? I don't even... Now I'm going crazy. I don't remember what the H gate is. Yeah, I was right. 1, 1, 1, negative 1. Okay, I'm not going crazy. 1 over square root of 2. 1 over square root of 2. 1 over square root of 2. Okay. This should be negative. Oopsies. All right, and then we have the 1, 0, 0, e to the I pi over 4. All right, so we have H, T, H. All right, so this is, we have H, T, H, H, T, H, T, T, H, T, T, and then we have H. Right, let's see what this is. Yeah, that looks like similar to what they have. It's in a weird form, but don't know if that's equal to H. I think this might just be a bug in the code book, but I'm not 100% sure. I don't want to do all of the matrix multiplication out. Okay. I guess I encourage someone else to do the math on this one because I don't want to do that. Okay. Prepare yourself. All right, this will be next time because this is already at, let's see, 30 minutes. So that'll be all this time.